Well, hello friends. Today we are going to take a look at memory profiling, and I would like to get to a place where we can record a program running for a while, and then we would have sort of all of the malloc events, all the free events, and mmap, monmap, stuff like that. And then we could throw those up in the profile viewer, and maybe we would start by just seeing the events laid out. But then I would like to also be able to turn it into a tree so we can see like how much are we allocating with each stack, stuff like that. But we don't have any facilities for any of this right now, so we're going to have to start with something. So I guess we can start with maybe in malloc itself. So I guess what we want to do is if a program is being like memory profiled, then we want malloc to generate some sort of event. And so currently malloc has a few different exit points, but it would probably be easier if we make this into a wrapper. So then we don't have to deal with all the different ways that malloc can exit. Okay, and then we do putter is this malloc impl size, and then if memory, something like that, then we will like profile, memory profile event, and maybe it would be something like memory profile malloc, profile event malloc. Maybe this just be a profile event, performance event. Maybe we can call these. I don't know. I don't know what this is gonna where this is gonna go, but we'll see. Perf event malloc. Okay. And maybe we'll also give you the pointer and the size. Maybe the size and the pointer in that order. That's kind of nice. Okay, and then let's do the same for free. So we'll say free void putter. This guy should really return the putter, and of course free is going to be renamed to free impl. Okay, and here we can just generate the event first, maybe. So perf event free, and we don't know the size in this case, but we know that pointer. And what does that mean in practice? It means that basically we're somewhere that this is going to end up in a recording. So I'm thinking we'll probably send this to the kernel, and then the kernel can gather these. And then if somebody is making this recording, then we'll put these in a buffer for him, and then he will have to match up like the mallocs and the frees. But yeah, it'll probably make sense. We'll keep going. So G profiling memory. Where do we want to store that? What do we even want that to be? Let's see. How do we learn that we are suddenly now profiling memory? Because I don't want to do like a syscall here just to figure out if we're profiling memory. We have get time of day, which is implemented as sort of a shared page with user space, but that's global, so we can't use that. We'll figure it out later how to set it, and we will put it into a full G profiling memory. Okay, and maybe we'll run with it always on for now. Okay, so performance event. We can call it perf event. Perf always reminds me of my old coworker Ryosuke. He was always talking about perf. Perf this, perf that. Okay, and then free impl putter. Okay. I guess we can do it after the fact, because that's what we do for malloc. Okay, so then we could have a separate one for calloc, actually, if we wanted to. Although, that's not really meaningful. So this is probably pretty good. We have realloc, but realloc just calls malloc. Okay. I guess we can do this with an environment variable for one thing. So like libc profile malloc. We can start it this way, and then later on we can figure out some way to like attach to a running program and tell it like, hey, start profiling yourself. But this will actually be slightly nicer, I think. We'll just, yeah, for prototyping this is better. Okay, so S profiling, we'll put it next to these other guys. And then we can make it static, all right. And perf event, I think, is going to be a syscall. So perf event. Really, it's like, yeah, perf event is good. We want to have like a generic mechanism where you can just say like, hey, some event just happened that might be interesting for performance profiling or whatever. And then maybe ideally the API would just let you do this. And I mean, like a final version of the API might look like this. And then this would sort of be a no-op if we're not interested in perf events in this process, or if we're not recording for some reason. I don't know. We'll see. But for now, let's do it this way. So what are we going to do with this? Syscall, we defined the syscall. Now we just need to define something here. Put it at the bottom of the syscalls. Perf event. So we had the type, like the event type, and then we had a size and a pointer. But maybe these should just be like this, like something like that. Like they could have 2 arguments. I don't know. We'll probably have to tweak this anyway. So let's stick with this for now. And let's see. And we should probably come up with some cool defines here. So like perf event malloc is 1, free is 2. Okay. And let's see, switch type. Maybe we will copy these into serenity.h, which is the user space header for Serenity specific syscalls. So perf event We'll just forward it to the kernel. Okay, that's good. Now, what are we going to do when the kernel gets these? So basically, the process has just informed the kernel that something that might be interesting and performance related has just happened. So we will have to take the information and store it. Be like if perf event, if we don't have a stream or a buffer, return enval maybe. And otherwise we will say like perf event buffer append maybe it can even be like this. This will just be, maybe it'll just be a vector, and then we'll say break return 0. Okay, something like that. And then how is this going to look? This will be something like, oh wait, perf event make it into a circular queue maybe. Perf event. Just like, how many of these do you want to store? We don't want to store these in kernel memory, actually. We want to store these in memory that belongs to the process, because we don't want the kernel to get blamed for some process using up a lot of diagnostic memory or profiling memory. So I think maybe we'll make a K buffer. And this will be the perf event buffer. And maybe this will be like, maybe it will be like this. Perf event buffer. Okay. Perf event buffer. Okay. Just say append, and then the perf event buffer. I'm gonna need one of these guys. Come here, copyright header. Boom. And let's see what we define here. So it's definitely going to need to have some kind of little struct, like a perf event, and this is silly. We'll make something like supposed to be a union. Malloc perf event, free perf event. size t, size, virtual address, or uint putter t, putter. Okay. I don't know, something like this, and then say int append okay. Blah 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 blah. So we need to allocate a buffer first of all. So we'll make one, like create with size, and maybe we will allocate 4 megabytes for this. It's going to be a very, very chunky buffer, but it's just virtual address space. We don't actually allocate physical pages. And these should really be like on demand, not always there. So let's see, process perf event buffer. Most processes are not going to be doing this, so we'll do it like this for now. Okay, and then well, actually we don't need that. We just need append type one. Okay, and then this thing needs to track how many we have, by the way. So size t m size. Or that's like the event, the count, I guess. Size t count. This is going to be a kernel result code, not necessarily an integer. So let's be clear about that. And let's say perf event at index. We'll do some magic with that. So okay, success in the normal case. Okay, so switch type. Perf event type event data malloc is dot putter is arch1 and arch2 is size and break. And in the other case, perf event free, then okay, and then default we return k result in val. Yeah, then we can do that checking here. Maybe that's nicer. Okay, and then we need one of these guys to be non-const as well. So maybe the public constant can just be like return const cast. Something like that. Then here's the real implementation. So I need to be a good boy and start using reinterpret cast more. So mbuffer datum. Okay, and then if index is greater than capacity, wait, we should assert this actually, since this is returning a reference. We'll just do it this way. Okay, and size t capacity const return. What is that? M buffer size divided by size of perf event? Something like that, right? That's our capacity. Okay. And here, if size if count is greater than or equal to capacity, return k result enomem. Or was that enobuff? Is that the one? No buffer space. Okay. Return events index. Cool. And so here we just do at count plus plus equal to event. Okay, so I think now we are saving the event. Maybe we will also log what we are saving. So we can do something like perf event malloc arch1. Maybe we'll do it here. Event data malloc. Better. That way they have the right types. Event data malloc size. And free only has the putter, so that's all we get to see. Well, that didn't even build. Perf event is somehow wrong. Cannot convert void start to uint putter t. Well, I'm sorry to hear that. Can I static cast that, I wonder? No? Well, like I care. I thought uint putter t was supposed to be convertible nicely, but maybe it's not. I guess we will just sling him a 0. Oh, here we need to append like that. And I guess we need to actually start saying that we want to record here. So mperf event buffer. If there isn't one, then we have to make one. Perf event buffer. Like that. Okay. Did I make it in time? Are these perf events, performance event, profiling events? Maybe performance event is the nicest name. Perf event buffer, I definitely don't like that. It's too, like, it's too weird. Perf. We can afford to spell it out. I just got a little carried away there. We'll rename it. No big deal. But before we rebuild because of that, we will, of course, test it out. Oh my goodness, look at all these performance events. So, seems like that S profiling is on. Because I turned it on by default. What was I expecting? But that's good. That means that we can see a lot of these things. So, let's rename the file. I'm going to see this one as a pointer, because I guess it was a uint putter type, so I didn't get it as a pointer anyway. Oh, the building. Don't we just love rebuilding? So we definitely don't want these for all processes, just one that we are profiling. So wait a minute. Why are we still getting it? Because I didn't sync the disk image. It looks neat though, that you can see like now this pointer was freed, now this pointer was freed, now this one, and so on. It looks like we're getting the size and the pointer mixed up here. Did I already forgot how I do that? How I did that? Malloc puts the size first and the pointer last. I guess that makes sense. Then these guys have to switch places. Okay. Why am I still getting the perf events? Because these things did not relink. That's so weird. Like, I changed libc and I have to build twice for things to relink. It's not right. Anyways, whatever. It's not a big deal. Things have bugs. So if we wanted to actually profile something now, what we would do is we would set the libc profile malloc environment variable. So we'll say like libc profile malloc is 1, and then we would run something like system monitor, and boom, look at that. We are getting all of these perf events. There are obnoxiously many of them. So many of them. A little too many. So, or it's not too many, but we definitely want to be a bit smarter about the way we store these. So we're going to make them new packed. It's 8 bytes, and then we take this. Well, actually, these guys. I mean, let's make everything packed just as a convention. But then this guy right here, he's 12 bytes. It's 12 bytes per event. So that's a little hardcore if we could get it down to 9 bytes. That's a bit better. It's definitely a bit better. So it's 9 bytes per event, which means that in 1 megabyte, we could store about 116,000 events. Well, we're probably going to have to allow bigger buffers, obviously, but it seems like a place we can start at least. We could definitely do this for like a small program. Like imagine that we wanted to run like ls, right? You wanted to see all the allocations that happen across a run of ls. Now we can do that. So it's good. But that's only 9 bytes. Now we're missing the crucial part here, the thing that makes this actually super interesting, which is going to take up so much more memory, which is the stack. And I can't believe I prematurely optimized away that 3-byte thing where I'm about to add like a huge stack to each one of these. But that's what we got to do. So let's see, that would be, what do we do for the profiling? For the profiling, we store the stacks as, these are the frame pointers, like these are the addresses, and these are the offsets into those addresses. Wait, what does that even mean? What is offsets used for? I don't remember. Offset slot. Oh yeah, that's how we store the offset for symbolication. Man, the profiling is not very efficient because we even symbolicate all this. We like figure out what the name of each function is in the kernel, and this is convenient and everything, but it ends up using up so much kernel memory when we could symbolicate in user space instead. Anyways, so we are going to need a backtrace, basically. So if we go in the performance event buffer and we want to add this, then what we want to do here is we want to say event dot stack is current. Can we get a raw backtrace? Booyah! All right, so this gives us a vector of u32, which should actually probably be a vector of uint per t. Now that I think about it, that's already what it was here. So we'll just commit that right quick. Kernel update thread raw backtrace signature to use uint per t. Yeah. Okay. So we get a vector. Now we don't need to store the entire vector with the event in the event stream, but just for our own convenience, we could do something similar-ish to storing the whole thing. So we can just do that. This stack 32. Okay. And we will then copy into the event stack from the thread backtrace is current backtrace raw backtrace. Sorry. We want to backtrace it from the EBP, but we don't have the EBP, but we can get it. I guess we want the EBP where we entered the kernel. kernel stack top. We have some hack somewhere that does this. Get register dump from stack, right? So can we use that here? Current get register dump from stack dot ebp. Slightly hackish, but that should give us the base pointer at the point where we enter the syscall, because otherwise every single performance event will appear to be like inside of the performance event buffer append function, which is, you know, not terribly interesting. So let's see, now copy to from thread backtrace.data. And this will be the min of size of event stack divided by size of uint putter t, and thread backtrace size times size of uint putter t. Actually like that. We'll even call it backtrace. Okay. And that means that we could also log the stack that we got. So let's see, we need to remember how many frames the stack has. Oh, this thing is growing so fast. We can store that as a second U8, I guess. Stack size. Something like that. Stack size is, it's going to be this right here, and then we'll just do that. Okay. Let's dump the stack. So for I is 0 to event stack size debug event stack I. How will this look? I feel like this is going to be very spammy. So we could definitely come up with more efficient storage schemes here, because now we're not going to fit nearly that many bytes anymore. So now it's 138 bytes per event. Holy moly. So that's only 7,598 events. We'll still be able to do LS, but like a longer running program, no way. But you know, one thing at a time. And then we might want to do some sort of scheme where like you're sort of streaming this to a file or something. You have some program that runs and connects to another process that's currently recording events and then saves them to disk periodically or whatever. I don't know. Not something we have to figure out right now. So let's see, profile malloc ls. That crashed in raw backtrace because I tried to read a very goofy address. Is this me trying to read that base pointer from the kernel entry point, maybe? 25 to FE3C 252. Wait, what's wrong with that? 252 fe3c. That's where we entered, isn't it? I guess I'm clacked. This is supervised remote access protection telling me that I should not read a user space address just like that, which is a fair point. So where did we do that? Hackery. So let's see, UNPRT, EBP, copy from user. Let's try that. Still no? Why can I not read from that address? 192 FECC. It's definitely in the stack. Raw backtrace. Oh, maybe we need to actually, maybe we need to turn off SMAP for this whole process. Crap. Maybe, yeah. Backtrace is not SMAP safe. That's a bit annoying. So we can do it like this. Backtrace. Let's just temporarily disable SMAP. SMAP disabler. Also, it's kind of annoying to have to type profile malloc on. Okay, here we go. Cool. These are our stacks. It seems like they always end in 0. So we probably don't need to store that. So if event stack size minus event stack size, I think we can do that. And that will give us slightly shorter stacks to deal with in user space when we eventually get there. Let me make an alias here. This or get np. Okay, so export p ls. Look at these stacks. Aren't they pretty? So that's pretty cool. Oh, I'm out of tea. That's gonna be a problem. Great. So what are we going to do with all these? I have to make a program that, well, first thing we have to do is transfer these to user space. And what's the best way to do that? I guess the best way to do it is that what's the easiest? Like when a program exits, if it has anything written, it could store it to a file. That's one option. It's a bit strange, but I also kind of like it. It's almost like dumping core. And then you could imagine like signaling a process while it's capturing performance events, and that would also cause it to dump perf core. So for our purposes right now, I think that would be the most convenient. So let's do that. Sys exit. So we'll do it when we exit a process. When a process dies, actually, because then we'll get it, even if you crash or whatever, we'll always dump out the perf events. So let's see, blah, blah, blah. Maybe when we finalize the process, so we tear everything down, close all file descriptors, la, 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 and then here we can open something up. So if m perf event buffer, yeah, we can leave that name for now. So where do we want to store this? This might not be the best solution in the universe, but I think it might be okay. So we need to do this before we lose which directory we're in, actually, because otherwise that would be a bit silly. So open in the current directory, we create a perf core. O-creat, O-excl, and the mode is going to be 400, read only. And the custody will be current directory. And the uid and gid is going to be the user who owns this process. Okay. So if we can't create that file here, then we'll just give up. Like if it would overwrite something, then we won't do it. Uid and gid. Okay. All right, hold on. How does this work? Description or error. Right. Is error, then never mind. So if it's not an error, volume description right. Okay, so how do we do this in the easiest way possible? Perf event buffer count. That. And maybe we should build a JSON representation of this actually. So JSON object serializer. Do we have that here? JSON. Probably we'll have to get it in. JSON object serializer. Oopsie. And I guess actually we're building more of an array. And then need to build this into something, so we'll make a builder. Array finish. And this thing needs to, wait, how does this work again? Okay, buffer builder, you just tell it build, right? Okay, something like that. We'll make a best effort to write it out, and if it works, it works. So here we would just start adding a new thing. Wait, how does this work again? Add object, right. The serializer class is really cool. Sergey made it, and I always struggle a bit to remember how it works, but once I remember, I really quite like it. So here we just add the name of the object, which is going to be type, and the type is going to have the type is going to have, why am I blanking? Perf event buffer at I. Event dot type. Oh, that's a private member. Crap. I didn't mean to make that private. Well, I wanted the const variant. Is that not good enough? Perf event buffer at. So just pick this one. Okay. Definitely missing something here, but what is it? Const at, okay. Why does that matter? I don't get it. Okay, well, we're not going to figure that out right now. Let's make forward progress. So then, in addition to the type, we also want the info. So say type is event type. This is actually kind of weird. We should put this in the helper. So JSON is m perf event buffer dot to JSON. Okay, that's more like it. And we can take these and bring them with us here. Okay. And of course now we are the perf event buffer, so we don't need to be asking this politely. And why do I constantly forget what's in this thing? It's either malloc or free, right? So I guess we want to be a little bit, should we be fancier about this? We can just use the numbers. Or we can be a bit fancier. Why don't we get a little fancy? We can unfancy it later when it turns out to be very, very slow and huge. Putter, event, data, malloc, putter, size. And do that, if it's free. And of course, object, add array, we'll start a new array, stack array, stack, and stack size plus j, add object. I mean, at this point, we can just add the frame value, really. So add and stack j. Stack array finish, object finish, return builder build. Okay, that was a lot of typing. I wonder if this will work. I've never tried something like this before, like writing out a file on exit. But it would be a good mechanism to get comfortable with, because eventually we're going to want to produce core dumps anyway. Template argument required for JSON object serializer. Well, I'm sorry. I guess I'll have to tell you that we're building a kbuffer. Kbuffer has no append. Kbuffer builder. Wait, what? What am I doing wrong here? Slab allocator. Why are you here? Why is there a forward declaration here? That's not even necessary for any reason. Is this ever templatized? Doesn't look like it. I feel like you should be able to just do that. So this is an ambiguous overload. Well, okay, we will just say that these are 64-bit ints. In your face JSON object serializer. Maybe I'll collect one good boy point and do this. Okay, so will this produce a file? I wonder. Oh shit, I guess. Well, there's perf core. We should unset p so that we can. It has a whole bunch of JSON in it. The parser likes it. Look at this shit. How cool is that? Let's cron it just because. Okay. That's really, really neat, right? So these are all of the allocation events, and malloc and free events in the ls-l program execution. And for each for each event, we know. Wait, I'm missing the putter, but where's the putter? Oh, I can't. I'm not scrolled to the top. Okay, so let's just look at the last one. So we have the size, which looks totally wrong for free. So that's a weird issue. But why do they look this way? Free size. Do they look totally... Oh, shit. There is no size for free. It's a putter. What am I even doing? Okay, so here we go. A little more sensible output, hopefully. Let's just try that again real quick. We can get rid of all that debug logging. Gron, curve core. Okay, so wait, free still has a size. Did I forget something? Oh shit! Yeah, right. It doesn't overwrite. It doesn't overwrite if there's already a perf core, so you have to remove it. I think that's okay. So id that debug spam. Very debug. I don't remember who started very debug, but I like it. It's like, I think maybe it was Conrad. If something is like very debug, then you don't want to hear it most of the time. Network task, Ethernet very debug. Probably Conrad. So can we just see? Oh yeah, that's a lot nicer. So it doesn't soak up a lot of time. And now we have our perf core, and if we cron the perf core, then we can see that the free just has a pointer. There's no size for the free, and of course execution ends with a bunch of frees, but for mallocs, we have a putter, a size, and a stack of call frames. Very cool. I guess metadata is the thing that I'm missing now, because like I don't know which executable this is from, so that makes it hard to reason about how to symbolicate this. So in the past, I would have just been lazy and symbolicated this in the kernel. But maybe I would like to not do that right now. It would be nice if we could symbolicate it in user space somehow. But for that, we need to know what the executable is. So we'll just do that. So we'll say, before we start serializing the events, we'll make an object serializer. And we'll do object add array events, something like that. Okay, and then object add executable. Maybe here we'll put the executable name. All right, and maybe the PID. I don't know. Maybe the PID is okay. Might be helpful. So we'll have to pass that along as well. PID, okay, to JSON. Finalize. Make sure that we pass in the and the executable absolute path, or we can just pass in the name actually. Is that fine? Yeah, that's fine. So then let's call it PID and name. So it doesn't have to. No. Name is not enough. We need to know the executable path, because otherwise, how are we going to open the thing for symbolication? Right. So executable path. And buffer, blah, blah, blah. M executable. And if we don't have one, then we will just say fnut. In Swedish, this is, people like to say fnut for these. Very, very strange. But I guess I just said it too, so. Fnut. So once we have the executable name and we have the JSON file containing all of the profile data, or all of the memory perf events, then we could load them up into the profile viewer. Now, I feel like it's not going to make total, it's not going to fit in with the profile as it currently looks. I mean, it has timestamps. Maybe we should put timestamps in there as well. Now that I think about it, why didn't we add timestamps? It's clearly relevant, especially since like it's not like a sampling profiler, so you might have like a long time before between two events. So timekeeping is even more important here. Timestamp. Look at this thing grow. Eef. Okay. So we can do that right before we store it. We'll do like event timestamp is curget or g uptime. Something like that. Okay, and then we will store the object add timestamp event timestamp. And rebuild over and over and over. Maybe we'll reserve 4 megabytes for this guy, give ourselves some leeway. Because I feel like now it's starting to get real chunky in here. But if we have this much divided by, what was it, 146 bytes or something? 28,000 events? You know, that's manageable for now. So let's take one last look at these things. I wonder if they would fit into our profile thingy at all. Because we can certainly show the events like that. Maybe we should try that. So I guess let me show you what it looks like when we just generate a profile. In case you haven't seen the profile viewer, it looks like this. Oh, that's a really terrible profile. It's so small. I thought 12 was Windows Server. It was. Okay, let me do something interesting then. Jeez. Okay. So this is what it looks like, right? These are all sampled stacks. And then if I select a range here, then I can see what was going on at that particular moment in the program. And here you can see the new naming scheme for library functions. I started putting things into namespaces. Instead of C event loop, it's now core event loop. I wanted to do that forever, so I spent like 4 hours doing it today. Anyway, would this work for memory events? If we could just show the memory events like this, and we could see the stacks down here, it would be kind of interesting. I guess maybe it would be a start. Although, like, the very first thing we need to do is symbolicate. So let's do that first. So should we do a separate program that does it, or nah? What if we just try to load it? So how does this thing load stuff? It's been so long since I've worked on it. Profile, load from file. So it's a JSON array. No? JSON value. Oh no, these guys are arrays, right? So we have a object, and memory profile is an object instead. What if we let's just try to do this. So load from perf core file. And so this would be an object. And let's see, auto. Wait, it has to be. I'm in the wrong place. Object is JSON as object. Pid is object, get pid to u32, and we have the executable path, which is the executable path. Is that what we called it? I already forgot. No, maybe it's just the executable, but I feel like it should have been executable path. Maybe executable is good enough. Okay, executable. And that's a string. Okay, and then we gotta open that sucker. So how do we do this? We need to open it with the elf loader, I guess. So do we even build the elf library for user space? I forget. With elf makefile. I would really like to have an elf library right about now. So maybe we can get one if we just tweak this makefile a little bit. Who's building these anyway? Elf image.o. libc does it. Oh shit. Wait, hold on. libc builds elf image. Huh. That's fine. So elf loader has the symbolication stuff. Does it need to? switch to user space mode. Sorted symbols. Maybe this could just live in the image. I'm not sure. It's a bit weird that it lives in the loader class, but maybe that's okay. Don't have to re-architect everything right now. But we do have to start building the elf loader into libc. Maybe that's not a big deal. Yeah, it's just built right in. Okay. So, elf loader. Does that give us elf image? Yes, it does. Okay. Cool. Executable. So, how do we do this? I guess if strcomp, we'll just do a hack here, but if you start it with perfcore, then we will do, what does this thing return anyway? I'll put her to profile, right? Take me back. Okay, we'll put that here, profile, and we'll say profile is profile. Load from perfcore file path. Else, do this. Okay, so, and we'll happily go into here, and we don't need the pivot actually, whatever. So we'll make an elf loader. And elf loader takes a raw elf. Okay, so we will memory map the elf. Mapped file. Elf file. Executable path, something like that, and then if elf file is valid, return false. Or in this case, we return null putter to signal that something went wrong. So let's see, debug or fprintf, unable to open elf, executable. For symbolication, let's say, and then elf loader symbolicate. That's how this is going to work. So we'll have to go through the. Wait, do we do the load? No, we don't need to do load. We just need to use the symbolication code. Because the first time we get here, it will allocate. Okay, I think this is going to work. So the samples is going to be object, or hold on. Samples is object get samples, or actually events in this case. If events is not an array, then bad format, sorry. And then we pass control to that constructor, apparently. What does it do, though? Because he expects to find strings. So this guy looks in the JSON array and he expects them to have timestamp, frames, not stack, and then symbol, address, and offset. So what we have is stacks or stack, and then for each event we have, this is for every address in the backtrace. I think these we can resolve based on the value of the stacks. So we have to produce this basically. So we got to take the input and turn it into this other format. We can do that. But we also have types of each event. And this thing doesn't care about that. So we'll get to that. But if we can just get these to show up at all, that would be cool. So let's massage the data. And I guess we can just call it samples. Profile data. JSON array profile events. This thing we can call perf events. And okay. Values. And then what do we have in this guy? We have the type, which we can ignore for now. We have the timestamp. So profile events. We want to create a new JSON object and then add it to the array. Event object. We can just call it object. So object set timestamp. This is going to be very inefficient, but I don't care right now. That's the perf event get timestamp. As object. So perf event value. As object. Okay, we're getting there. We have to deal with the nature of the polymorphic nature of JSON values a little bit. Okay, so we need the timestamp, and then we need to start doing the frames, and this is going to be another array. Frames array, which we're going to produce. So JSON array, frames array. And here we'll do for auto frame or frame in perf event get stack as object. Wait, it's an array. Perf event stack array. Ugh, this is not beautiful. My nose is so itchy. Why? No viable begin function. Well. Maybe we don't need that as a temporary. It's kind of ugly as a temporary. Can we just do if we can just do it this way? Then this is slightly nicer. Okay. So now frame has, I already forgot, perf event buffer. Each frame has, oh, it's just a value. Shit. Okay, so it's not, it's just a, a pointer value. So we got to symbolicate that. Putter is frame as U64, or 2U64 even. Oh, there's no such thing. To number U64, that's how you do it maybe? Okay. And then putter, symbol is floater, symbolicate, putter, oh, and we can get the offset, right? So frames array and move frame object. Set address. The address is the putter. Oops. The symbol is the symbol, and then the offset is the offset. Okay, I don't know if this is gonna work, but let's just try it. No matching function for floater with no input. Ah. Right, I need to give it an input. File data, file size. Okay, I'm sorry. Const u8 star. Is that better for you? What does this give me even? Oh, const void star. Okay. I'm gonna maximize my good boy points here and use static cast. Because I realized lately that I'm using too many C-style casts, and just because I know what happens when you do a C-style cast 99% of the time, it doesn't mean that the code is readable for someone who's less familiar with that. And I would like to write more readable code, so that's just one of those things that improves that, I think. And it's better to be explicit about it, about your intentions. And that 1% of the time that I do mess them up, that's not good either. So let's see, export p1 ls, and we died. I cannot append to my performance event buffer. Why is that? That's weird. I would have expected that to be quite small. I don't know why that would happen, but okay. Let's just assume that that was a fluke. It seems like maybe that's not a fluke. Okay. Performance event buffer. Is 4 megabytes too much? What the frick? Oh, is this JSON getting gigantic or something? This is even the wrong buffer anyway. Okay, buffer builder, JSON object serializer. Okay, buffer builder uses how much? 4 megabytes. And has space is failing. Why? What did I do? I added the timestamp. Did that make things too big? What if I just made that even bigger? What would happen? Hypothetically. Okay, so it's... Oh, wait. What am I doing? It still dies. Well, that's rather strange. So let's see how much we're actually pumping out then. Because we shouldn't be pushing out 4 megabytes of this crap. So are we just looping forever or something? To JSON. Object add. We are crashing in finish. Here. Okay, so let's just see how much we have at this point. So finishing object with builder size, the buffer builder. And how much does that want to add? Just 1 character. 1 character is too much. Something about this doesn't make sense. So I have appended 80,000 bytes, and then it says that it has no space. Well, color me suspicious because I don't trust that. So, okay, buffer builder. Has space and buffer size. Guess we're gonna have to do a little bit of printf debugging here. So it has space is m size plus size less than and buffer size. Like that. All right, now tell me your secrets. Oh my god, that's obnoxious. Okay. Okay, I cannot deal with that running so often. So if current process name let's say if current PID is more than 10, then we'll do it. Okay, now we're sophisticated here. Wait a minute. Why did that work? Oh. Has space. Oh, it's the wrong page. Okay. We're in finalizer. Okay. So, I guess this is very explicit, but what is it even logging some of those times? Finishing object, right? So we should just let it get to 80,000 or whatever. I think if I let it run without me looking at it, then it goes way faster. It's funny though how you can get so slowed down by output. See, I feel like this number is always going to be less than this number. So why would it suddenly switch over, I wonder? All right, come on now. Get to the 80 whatever. And we died. Right here. Because the size is suddenly exactly snug to fit. Fine, but why is it like that? Finish. Do we set the size of this guy somewhere? Set size. Yes, we do when we call build. And we set the size of the buffer. So after we call build, we really can't use it anymore. Finishing object. Builder build. Set size. Return buffer. Does this guy do something when he goes out of scope? Oh shit, wait, hold on. Oh, I'm not finishing this one. Oh, that's so weird. That's a funny bug. So I guess this guy right here, when he's destroyed, if it's not finished, then it will finish, which will append one more character, and that's what we're seeing. Because the serializer here is created before the builder, or after the builder, but it will be destroyed on exit. So we'll build, and then we'll unwind, destroying this, which will append. Okay, well, that's a funny problem. So object finish. And let me make less of a mess. And there we go. Okay, did I sync? Yes, I did. Okay. So export p1 id unset p ls jp perfcore. Can we open this, I wonder? That's crashing. Okay, so why did we crash? Crashed in load from perfcore file, JSON value to number, and we are doing a to number here. I wonder if it's this guy right here, if we are doing something real sneaky like. I think maybe this isn't cool to do it this way. We may have to actually store that thing somewhere. So stack array that and stack array values. What is that? DevTools profile view. Okay, progress, I suppose. So now we are in the profile constructor. We're trying to read past the end of a vector of JSON values. That's something. probably it's here. So maybe we should say 4 is, or should we just massage it so that it looks like the other format? I can't decide. Like right now we can just massage it, I guess. So in the other format, it's like going backwards and skipping one frame. But we skipped the frame in the kernel, which, you know, maybe we should just not skip that frame in the kernel just to make this easier for ourselves. Or we could also add, we could synthetically add one. It's a bit stupid. Let's just not skip that frame. For now. And after we get a profile, after we have a perf core, we should probably save it so that we don't have to keep regenerating it. JP perf core. Okay, so we are failing in vector at. That's fine. Perf core. Wait a minute. Hold on. Oh, right, I can't do that myself. Okay, and then this is looking okay. So I wonder where it falls apart. We can just maybe just do something somewhere. We can do a little bit of logging, see what's going on. So how about we log here, debug, parsing a sample of JSON values. Write down size. Something like that. I feel like we just parsed 0 values, so did we even produce anything? No, I'm not sure anymore. Profile. Profile events. I'm never adding anything to the profile events, of course not. So if we pass in an empty array, then it will indeed not do anything. Okay. Now we are failing somewhere more interesting. As U32 says, this is not a U32, you jackass. Okay. Maybe we should just do the pointer as the 32-bit value for the moment. Let JSON value become 32-bit. Oh. Sometimes the disk image does not want to boot. And we make a new disk image. And then it wants to boot. Oh shit, look at that. So what on earth are we looking at here? Let's turn it around. So these are either malloc or free events, basically. and the names are mangled, but we did symbolicate them. That's fucking cool. I mean, frickin' cool. So we don't know if they're malloc or free, but we have them in a tree. That's pretty nice. So, and we're aggregating by Callstack. Very interesting. So I feel like we're losing some information here though, because like where's malloc? Free, right? I just see that we're in like vector of string clear, but we are losing info. Performance event buffer. So maybe using the EBP was not the best. The EBP. We could grab an EBP where we are. So we do that in a bunch of places. So we do something like, we'll just do like this basically. And that will give us wherever we are in the kernel, and we'll use that. Let's also demangle those guys. So demangle works how? I forget. Demangle. Why does it not demangle? Oh, demangling does nothing in user space. Why does it do nothing in user space? Demangle. I feel like someone turned it off. Andrew turned it off. For some reason, the default CXX flags and such don't get us demangle in user line. Well, I really want demangle now, so let's pray that it just works. And we're gonna have to regenerate that file so that we get a deeper stack. I was kind of hoping to avoid getting the kernel stack, but maybe it's not the end of the world if you see the whole stack, actually. We'll see. Let's see. Okay, I just have to leave it alone. Okay, well, first thing is, if we just do this, do we get demangled names? Yes, we do. So that just totally works. That's awesome. Okay, so at least that's not a problem. Where is that? Ack demangle. Turn demangling back on for user space. This didn't work at some point, but now it apparently works again. Okay, and then we wanted to make that new recording. So we'll remove the old one, say id, and there's our perf core, and this guy should now have some pretty chunky things. So we can't see the kernel frames, but we can see malloc. So because we're in user space, we don't know how to symbolicate kernel stuff. So I think that's okay. We could actually just show them as addresses instead of question marks, but whatever. But this is really cool, right? Because now you can see that this is a malloc and this is a free. So now they sort of self-segregate. Man, that's really, really awesome. How cool is that? So we can see that we're hitting most of the mallocs in this program in ID are from string creation. So who's doing that? It's when we're splitting strings, when we're parsing the etc group file. Look at that. So 206 calls to malloc from string creation, and 141 of them come from grgid, get group by group ID. So I bet you that we could very quickly reduce this number by, let's see, where did we do split? We could use split view here, which will give us string views instead. But that breaks here because we can't split view on a string view, but we can split view. We can't split on a string view, but we can split view on a string view. That's kind of interesting. And then oh, but then these guys are all okay. I don't want to mess with this now because I'm not in the put the null terminator in the right space headspace, so it's better not to. But clearly, there's like a way to do less of these allocations, right? And that's interesting that we see that looking up a UID or a group ID in the password and group databases actually ends up doing quite a lot of mallocing. And then we append, that's also from the same place. I mean, this is the ID program, right? So it's bound to have a lot of this stuff. Interesting. So I just want to try this on something else. So what if we ran it on, I don't know, what's an interesting program? Terminal. ls, and we'll exit. And then we have a slightly bigger perf core. And what did we get now? Oh, right, we have to turn it around. I feel like we just got the shell. Oh, right. So because we exported P and we started a terminal, then the terminal spawned a shell, and the shell exited before the terminal did, so the shell wrote out this file. Okay, so some tricks around this whole everybody uses the same file name. That's probably not the best scheme, but we'll have to come up with some solution for that. But right now, I think this is okay. But then let's just start something that doesn't spawn another process. So file manager. Do a little bit of this, a little bit of resizing, and we'll exit. And did we crash? Yes, we did. That JSON was apparently too big, and this time I can believe it. So let's make a smaller one then. Jeez. P1 to about. Beautiful. Onset P. Okay, turn that guy around, and these are all the mallocs and frees in the about box program. So this program right here. Obviously, we still want to massage this data a lot more so that we show, it would be interesting to show like allocations that are still around as opposed to like things that were allocated and then freed. So you would have, we would like run it in a mode where it would prune any malloc that has a corresponding free. It would just prune both of them. Right now, we don't do that, but that's something that we should do. I'm just curious what's going on in here. So a lot of mallocs happen, most mallocs are in the iServer connection. So this is the connection to the Windows server. most popular one is, what is that exactly? I guess it's dispatch event. It's calling drain messages from server. Oops. That was right there. Maybe it's this vector here. Could that be it? Bytes. Yeah, we could maybe. There are probably things that could be done here to reduce allocation, but I mean that's not terribly much. Although I imagine that it's quite a bit more if you start to do stuff in a program. The about box, it just brings up a window and does nothing with it, right? Deferred invocation, that's an allocation. Would be nice to do that without an allocation. Byte buffer grow. Look at that. We are creating a string. I really love this type of stuff. Like just looking at how a program behaves using profiling information. So can we filter this in? Yes, we can. See, now we only see what happens in that particular time frame here. So in that particular time frame, we only had these mallocs and these frees. So I think we should do the smarts where we prune anything that doesn't have a corresponding thing. And maybe we should merge them together instead of being separate malloc and free. They should only be the malloc essentially. So we should show only the mallocs and then the frees should go away. That would be interesting. But I feel like we should commit what we have so far because we have built a few things. So profile, CPP, we don't have to log that thing that we were logging there. So it's kind of spammy. Okay, so kbuffer builder. What did we do to kbuffer builder? Just debugging crap that we don't need. Slab allocator, we removed some forward declaration, right? Kernel, remove unnecessary forward declaration in slab allocator. All right, and what else? I guess we can do the kernel changes. Don't need that anymore. And okay, kernel. Start working on a mechanism for reporting process performance event logging. Perf event, this patch introduces sysperf event with 2 event types. Perf event malloc, perf event free. After the first call to sysperf event, a process will begin. We'll begin. We'll keeping these events in a buffer. When the process dies, that buffer will be, wait, does that fit on the same line? Yes, it does. Will be written out to perfcore in the current directory if unless the file name is already taken. This is probably not the best way to do this, but it's a start, and we'll make it possible to start doing memory allocation profiling. Libc. Oh, we should probably, oh, well, we can keep that P thing. Allow opting into malloc and free performance event logging. If a program is started with libc malloc set environment, it will now generate perf event malloc and perf event free. There's also, oh, well, we can remove the shorthand because I regret adding the shorthand. P is too short to reserve for something like this. So libc profile malloc, that's okay. Okay, and let's say profile viewer initial basic support for loading perf event perfcore files. Perfcore file is the file that the kernel generates after a process that recording performance events has exited. This patch teaches profile viewer how to load and symbolicate those files so that we can look at them. This will need a bunch more work to make it truly useful. Okay. So I guess just when it comes to this now, we wanted to do the pruning, but it's good to have like a raw mode where you can see all the events like we can there. But obviously we want to see something maybe a bit more interesting than this. So how do we do this? We want to go through, like when we have a selection, then we're choosing which things are visible. And then we should have a special mode. Well, first thing, we need to keep track of like what type of event each of these are, because right now we just throw that information away. So it's going to be sample.type is get type to I32, say U32, whatever, and the default value is going to be ff, which we will use to mean, oh no, we'll make it 0, actually. That's okay. We'll say that 0 means not a perf event. So type and then, wait, are we even generating that? We need to store that. Set type perf event get type. All right. And then profile model. Profile model has something, or where's the thing that filters? Frick, I forget how this works. Profile timeline widget. When you mouse down and you mouse move, and we set the timestamp filter range on the profile. And then we rebuild the profile tree. Okay. So let's see. So here we're going from left to right, or like from the start to from the start to the end in the profile. So at this point we can like track each pointer, I guess. So we can. It's gonna be kind of weird, but okay, we'll do it. Hash set. U32. Oh, it's not called hash set, it's called hash table. Hash set is what WebKit calls it, but here we call it hash table. It's not the most important difference in the world, but live allocations, let's say. And sample type is perf event malloc. We're going to need the serenity.h. Then live allocations set. Sample dot frames. Wait. What is it that I want? Is it the first? No, I want the footer. Right. Sample dot footer. And else if sample type perf event free remove footer. Okay. And we're probably going to need to separate this logic a bit for like time profiles and memory profiles. But at the moment, we can try to push forward sharing the code, and then we can break it apart once the logic is a bit more mature. Because I feel like right now everything benefits just from iterating on it. So sample, where's the sample class? Right here. So we'll store like the footer and the size TV size, and we'll take that. Okay. Okay, so now we are keeping track of if something is live or not, and then I guess we're going to have to make a separate pass, actually. So first we make a pass figuring out which pointers are actually live. and then we will make another pass ignoring any pointer that's not live. So if sample type is perf event malloc and live allocation is contains sample putter. Continue. Skip over that guy. Yeah. And if it's a perf event free, then we can skip it entirely. I just want to see what that looks like. Isn't programming fun? I freaking love programming. Okay, so, oh wait, this is the old file. Now we have perf core, and we can open it up. And what do we see? Well, we see mallocs and frees, so that part is definitely not working right. I'm guessing that we don't store the type properly. Where were we storing that? Let's see, debug, sample, type. And sudo mount, sudo copy, sudo chown, umount, and okay. I just want to take a look at the sample types, see if we're actually transferring them from the input. Sample types are always 0, so that's definitely not good. And it's from the input that we get, so perf events, no, what did we call it? Profile events. It's not the best name. So, oh, right, they're named like this. Right. Well, that's a bit silly, but okay. So, then that explains it. So then they're like malloc. This is so wasteful. Why did we do it this way? It's so stupid. I immediately regret saving them that way. But let's just live with it for now. This is not premature optimization school, so let's survive this situation. And type is going to be a string. Get type to you. Where are you? To string. All right. Type perf. Look at us with our stringly typed programming. That's so gross. Shameful what I'm doing, honestly, but it's all about progress right now, and let's make some. See, now we're collecting the sample types. And now no pointers are live. Which probably makes sense since we exited, so we didn't leak anything, but the fact that we still don't show anything here is kind of suspicious. So, why do we believe that no pointers are live? Perhaps we are not storing the putter values. That would make perfect sense, since I probably forgot to do that too. Yeah. So sample putter, if sample type is malloc. Oh my god, this is so gross. Why am I doing this to the computer? To number U64. Although this thing is using U32 already, so let's be good boys. Else if sample type is free. Oh my god, it's just more and more of this. But for malloc, we also have the size. All right. I just want to see that something cool happens if we can see only the allocations that are still live. Well, there was something there for a moment. Wait, what? I'm not even sure what's going on here. So what if we look at that particular range? I mean, it doesn't make sense that there would be nothing. So like, what if we remove it and then we do like about, and then we go and, oh wait, hold on. Profile malloc about. What if it crashes, right? What if like things just go wrong and it gets murdered? And we now have a perf core file that was taken and it didn't end well, so like it didn't have a chance to deallocate. I think we're not doing this right. So should definitely still be things allocated, I guess is what I'm saying. Sudo mount cp. But I guess we can take a look at it. So do we have cron? Yes, we do have cron. Okay, so we can do like cron grep malloc and free. Okay, so there's like about 100 more mallocs than frees. So if we don't set a filter range, then we should definitely see some allocations. Live allocations. Show me the things. What do you think are the live allocations? Program? I just want to hear it from you. You think there are no live allocations? Well, I suspected as much. Well, why do you think that? Sample type is not malloc, nor is it free. Debug. Sample type is. What are you then? What are these? With putter, sample putter. We are going all in with the printf debug here. Putter is always 0. Okay, well, interesting. I guess that means that we didn't do a very good job of Wait, did I just call it putter when it's actually called address? Because I'm just an idiot. No, we save it as putter here. Okay. Okay, so that's not the problem. And if we JQ these, it's putter here. Add putter. Oh, but are we not storing the... Dang it. Gosh dang it. Alright. This massaging the data between the old format and the new format is really biting me in the ass over and over and again, and it's just my own fault because I keep thinking that reusing this code is better than not reusing it. And maybe it is, but I keep making these dumb mistakes. Alright, now we can see all the allocations that are still live when we crashed. If we select here, there, this should show us only the allocations that are live, still live, at the that were allocated from here, ending at here. So I think that's pretty interesting. So what is still live? I mean, actually, if we crash, what is live? Let's find out. Strings are live. Some UI registration strings. That makes sense. What else is live? A weak pointer to a core object. So the first time that you create a weak pointer to an object, then it creates like this helper object, and that's what we see here. So it's like the weak link, I think it's called. I guess this is like appending a child. Wow, these stack frames, they look so pretty. I really like the namespace, how the namespaces look. Very, very tidy. Didn't convert all the libraries yet, but how neat is this? How cool, honestly. So let's make a new one. Profile malloc. And oh, we have so many programs. Which one do we want to look at? How about paintbrush? I want to see paintbrush. Draw something. Okay, we'll exit. And there's our perf core. Let us check it out. It's a gigantic file. Guess it might take a moment to load it. Or 2 moments. Or 3 moments. Wow, we ran out of memory. Ran out of kernel memory. That's crappy. Alright. I guess we'll have to look at something else. So you see why I want to do memory debugging, though, right? Because we have some memory issues. Profile malloc 1. What can we look at that's not that chunky then? Jeez. I would like to see system monitor or file manager. Let's do file manager. Let's just exit it right away. Oh, it got even bigger. Frickadick. You know what? I'm not going to be able to open that file. I guess we just have to settle for something small then. Jeez. Okay. How about Minesweeper? All right. 1 megabyte. Can we do that? Please. I just want to see if Minesweeper has any leaks after it exits, because that's basically what it will tell you right now. If you don't select a range, it will tell us what was still there when we exited. And it seems like there's a whole bunch of stuff there when we exit. Could that be true, I wonder? PNGs. Who's loading PNGs? Field minesweeper main. How do we exit? Like, do we exit from the main function? I guess we, window close request is sent, which ends up sending a close request to the window. And then that causes what to happen? Close, hide, and if the app has no visible windows, we call did delete last window, call event loop quit, exit requested, at which point we will return from event loop exec, which is called by gAllocation. Aha. Aha. So we actually exit. So we leak everything when we exit instead of clean up after ourselves. Well, isn't that a revelation? It'd be kind of interesting if we didn't do that. See what happens. Live allocations. This thing is highly spammy. Also, if I didn't have like all these strings, then maybe it would be able to handle slightly larger profiles. Oh, but I wanted to rebuild libgui just to see what happens if we actually allow main to return rather than just doing a hard exit syscall. Okay. Right, so let's get rid of that. And oh, and we have some assertions when we exit. I wonder if we get that in everything. No, maybe we can handle it. Okay, so let's say that let's see profile malloc 1 minesweeper exit. Oh, yeah, see, that gave us an assertion. It doesn't clean itself up very nicely. Own putter to square label. What's going on in that class anyway? I have not looked at that for a long time. Square label. Square button. Ooh, raw pointers. I bet that we have bugs here. Look at this raw pointerage. Yeesh. Square label. Yeah, these things need to be managed correctly because these are widgets and we are not managing the ref counts correctly, so we get bugs. It's good to learn about that, but that's not why we're here. So libc, wait, is it already set? It's already set. Okay, so let's just do about. Wait, I have to remove the file first. That file thing is annoying. Okay, so exit it and then see the about app. Okay, so we exited cleanly, and this is stuff that's still around after exit. So what's in here? It's like static, global static constructors. some string that was allocated in event loop quit. That's curious. Well, various strings, not many, but a few. It'd be interesting to find out why they are still around. More like static, global constructed stuff. A vector of IPC messages, that's okay. Like event loop globals. I guess these are mostly globals. Yeah. Interesting. Quite interesting. So I guess the remaining piece now is to show how much size we're talking about, because this is like, it's just the number of allocations. But you know, I'm just gonna leave something for next time, because this is starting to get really, really long, and it's not, don't have to solve everything in one day, so. Yeah, we're just gonna check that it still works with the old format. So profile window server a little bit. Oopsie doopsie. And it still works with the old format. That's good. Ignore this crash. That is unrelated crap. Okay, so profile viewer. Wait, what was this change here? All right, keeping track of the live pointers. Keep track of live allocations. Only show unfreed. Only show live allocations by default. Now keep track of which allocation for memory profiles. We now keep track of which allocations are still live at the end of the selected timeline range and only show those. This is really cool, I have to admit. Okay, so I think this is going to be the end of today's video. So if you made it this far, then I thank you for watching and for hanging out while we implement malloc and free profiling, so that we can learn if there are memory leaks, and we can learn about memory usage behavior in Serenity programs. I think this is going to be a really, really good tool for improving the system going forward. And yes, it still needs a lot of work, just like the time profiler, but I think we have a very solid building block here that we can continue with. So I hope you saw something interesting today. And yeah, if there's something else I would have to say, I would say it now, but I don't have anything else to say. So thanks for hanging out. I'll see you next time.